So it was nice to come back to Dayton, Ohio today to sleet and snow. I was in Dallas, Texas yesterday. Yeah, at the data science is good stuff. Lots of jobs in data moving forward. Anyways, yeah, so we were in Texas. They had the gala last night in the Cowboys Stadium. Yeah, so I did in fact kick field goals on the turf of the Dallas Stadium. Yeah, it's a bucket list item, so got to do it. And it was 80 degrees and sunny, and then we came back here. So, all right, so what I am pulling up now is I'm pulling up just a reminder that we are finishing up today course material for exam number 2. Okay, so we'll finish up derivatives in mechanics of materials. Okay, and that means that the exam number 2 solutions that are now posted, okay, are really ready for you guys to start prepping. So, you know, the homework, in fact, just got off the plane actually around 12:30, 1 o'clock. So I've got to post the homework still for this week, but that homework will be on mechanics of materials. So here's what we did last year. Okay, on exam number 2, if we can find that in a way that we can see it better. Here we go. Okay, so again, the exam will be 5 problems, 20 points apiece. Again, 3 exams previously posted. Topics covered are everything since the exam number 1. So the first topic on that is sinusoids. So last year it looks like we started out with an electrical sinusoid, right? Frequencies, phase shifts. You know, here's an addition of 2 sinusoids. Can I write that as a single sine or cosine and find a magnitude and a phase? Understanding amplitude, frequency, period, phase angle, time shift, all of those things. And then being able to sketch by hand, right, and indicate things like the earliest time when the voltage is 0 or maximum or whatever. So you guys get the gist, sinusoids. Next topic. Systems of equations. Okay, looks like we did a dynamics problem with forces and things last time, but the ability to solve 2 equations, 2 unknowns by brute force substitution, but really more importantly, writing things in matrix form. All right, AX equals B, being able to solve by matrix algebra. So basically we mean inverting the matrix, X equals A inverse times B. For a 2x2, we want you to be able to do that by hand, and then again, the fastest method for a 2x2, the Cramer's rule. So you have a problem like that. And so those are sort of non-calculus topics. Then we move on to derivatives. Okay, and so you think about the applications that we've done here, right? Derivatives in dynamics, derivatives in electric circuits, derivatives in mechanics and materials. All of that stuff will be on the exam. Here's what we did for an electrical application. It looks like an exponential multiplied by a sinusoid. Okay, and so it looks like a product rule type derivative. Determine the value of the voltage at the first 2 points. The current is 0. Use your results to sketch the function. Okay, so again, the ability to find the flat spots, understand the concavity, sketch the function, all those kind of things, important stuff. And then as promised, absolutely sketching type problems, right? Problems where there's no equations, but you're using the real understanding of derivatives in terms of slopes and to be able to sketch. So here's an acceleration. Knowing the velocity is the derivative, right? Sketch the position if the minimum position is given here in the final that. So you'll start by sketching velocity, then use the velocity to sketch the position. And then here's one. Electrical, right? We did inductors and capacitors. Here's a capacitor problem where I is C dV dt. Looks like a current is given. Being able to use that to sketch the voltage. And then the power, right? The idea that I can multiply 2 graphs together. Okay, and keep in mind, right, units, things like should it be milliamps, should it be amps, those kind of things you want to have sorted out. And then finally, again, the topic we're finishing up today. Looks like here we took a beam that was pinned at both ends and put a sine wave on it. Okay, and so again, same kind of problems we started last week, we'll finish up today. Beam deflection, being able to calculate slope. Where the deflection 0, finding the deflections at specific points, in this case where the slope is 0, and then ultimately sketching the deformation. So all these different contexts, right, that we've been covering for the past several weeks, but really the concepts are all the same, right? It's derivatives, it's slopes, it's flat spots. Can I use that to sketch functions and answer physical questions about the behavior? Okay, so that's it. Again, this is just one of 3 exams posted, including my own handwritten solutions, okay, to every one of these exam problems. Okay, and the correct procedure to prep for an exam, if you want to get the most out of it, is not to study the solutions. All right, it is to download the exam, including the solutions, put the solutions away, sit down with the exam, and take it without the aid of the solutions. Go back and grade yourself. How would I have done on this exam? Okay, and if you do that, if you have your crib sheet ready before that, and on the crib sheet, I've talked to a number of people since the first exam, talked about how do we do better if we didn't like our grade. Okay, and talked to a student today that said, well, you know, my crib sheet had some formulas and all that. I didn't have any problems worked out. Work out problems. Put worked problems out on your crib sheet. Okay, whether they're homework problems, whether they're old exams, whether it's some of these posted exams. Again, if you're going to use these posted exams as practice, then putting these solutions on your crib sheet's not going to help with that process a whole lot. Okay, so, but other old exams, the TAs and the review sessions will pull up more old exams. I mean, whatever you want. You're allowed to write down anything as long as it is handwritten on the crib sheet. Okay, so just make sure you're ready to go. Take these exams, and then if you do that, look, we got this weekend coming up. We got the weekend after that. Right? And then the review sessions that week. So I think it's a Wednesday night, November 6th, I think it is. So 2 weeks from yesterday. It's an eternity. Right? So no matter where you're sitting now, your level of understanding, you've got time to get it sorted out. 280 Joshi, as much help as you need. Right? Come to my office hours right before class if you need to, and be ready to go for exam 2. Questions on that? All right, so we got to finish out then the material for exam 2. And of course that means next week we start what? Integrals. All right. If you think there's a lot of applications of derivatives in engineering, probably multiply that by 10. That's the applications of integrals. I'm sorry? Okay, so the point is integrals, you know, we'll get into really what that is. If you haven't had calculus, it's a brand new topic, right? And so we'll get into that from a very basic standpoint next week. But the amount that we use integrals in upper level engineering classes, it's constant all the time. Just about every piece of theory that we develop, we've got integrals in there. Okay, and so it's important stuff. And if you have a fundamental understanding of derivatives, it's pretty easy to make that shift and go to integrals. Right? If you've had some calculus, you already know there's a connection between the two. If you have not, we're going to make that connection for you next class. Okay? All right, so that said, moving on, we're going to talk about deflection of beams, more examples. Okay, so we'll just go on again with another example from ME 3120, Strength of Materials, also BME, okay, 3430. Which is the BME version of Strength of Materials. Okay, and what we'll do is we'll look at what's called a simply supported beam. Simply supported beam with a center load. Okay, and so what does this mean? Okay, so simply supported for a beam, okay, basically means that the ends are pinned. Okay, and so here's what I mean by a pinned end. Okay, I've got essentially hinges at the end so that if this beam wants to deform in some way, it is free to rotate at the two ends. Okay, and so if I put a load right in the middle of a beam, okay, the nice thing about these beam problems is they're pretty intuitive, right? Even if you're not a mechanical engineer or a biomedical, you're an electrical, engineer. If you take something like this and you put a load right in the middle, this is y and this is x. All right, pretty easy to understand what's going to happen, right? When I take this thing and I put a load in the middle, it's going to deform down like this, right? So I get a sense it's going to curve down. Probably the maximum deflection will be where? Yeah, probably right in the middle. It just looks by symmetry that's going to happen. Okay, and so you can sketch the basic shape of this initially. It's going to do something like that, right? And so this is my y of x. Y is a function of x, the actual deformation. And it turns out the answer for this guy is as follows. It's p divided by 48 ei. Okay, and then this guy's a cubic polynomial. It's 4x cubed minus 3 L squared times x, okay, like that. And so it turns out that when you have beam problems that have point loads on them, okay, that you actually have an equation that's good everywhere in between point loads, right? So it turns out that this is the result for the first half of the beam. 0 less than or equal to x less than or equal to L over 2. Okay, and so L over 2 then is where this thing's located, right? The entire length of this thing is L, and that's why we call it a central load. Okay? So, I mean, if this is going to be symmetric because the load's in the middle, then if I have the equation for the left half of it, then obviously if I want the answer on the other side, right, I just flip it about the middle. Okay. So, that's what we have for the deflection y of x. Okay, and so what would we like to know about this problem? Want to find a couple things. Okay, part A, I want to find the maximum value of the deflection. Okay, so we'll call this y max. Okay, maximum deflection. And then also, I talked, I think, last time. A lot of times we use beams to model things like shafts, right, in power transmission. In mechanical engineering, for example, I've got a plant, I got to transmit power, I've got motors, even in a vehicle, right? I got a drive shaft that needs to transmit power from the engine over to the wheels, through the gears, okay? And the idea is that if these shafts are transmitting loads at gears, then the shaft itself, even though it's a round bar that spins, it's got transverse loads on it. It's going to deform, right? And that shaft is supported at the end somehow. If you think of an axle on a vehicle, for example, the wheels are attached, there's bearings there, okay, bearings that allow things to spin, and those bearings, they can do a little bit of give like this, but not a whole lot, right? They're designed to have a certain range of motion. So one of the things I'm interested, besides just how much does this thing deform at the maximum location, okay, I'm interested in what's this angle over here at the bearing. Right? Because if I try and do too much at the bearing here, I can damage the life of the bearings. Okay, so pretty practical kind of things. So for this reason, I might want to find the slope, okay, at the end, right? So for example, x equals 0. All right, so a couple ways to think about this problem. If I want to know the maximum deflection for this problem right here, do I need to use calculus to do it? Any thoughts on that? So you're saying by inspection, I can see that the max is going to be in the middle. Okay, that, by the way, that's a symmetry argument for this problem. This whole problem is symmetric. It's a curve. So the only way that works, right, is if this thing here is symmetric about the middle. Okay? Great. So I could just plug in L over 2. But since this is an example of derivatives, and we're going to need a derivative anyway, right, because I want the slope, which by definition is the derivative, why don't we see whether or not calculus tells us what we think, right? Because if this is the maximum, then this should be a flat spot, right? And the slope should be equal to what? 0. So we can at least see if that'll happen. All right, so we'll go ahead and take a regular calculus approach to this, even though I can see by inspection the answer should be x equals L over 2. Okay, but y max will occur when the derivative, right, when dy dx, which is by definition the angle theta of x, if the angle's small, when that thing is equal to 0, that'll give me the flat spot. So first thing I need then is dy dx. So I want the derivative with respect to x of this entire guy here, p divided by 48 ei. And then I've got 4x cubed minus 3 L squared times x. So help me out here. What do I do with the letters out in front? P over 48 EI. It's just constant, right? These are numbers. This P could be 100 pounds. Anybody recall what is this E and I here? Elastic modulus, the E, right? The E is this thing made out of plastic or is it made out of aluminum? That affects the E. And then the I is affected by what? What's that I called? Anybody remember? It's the moment of area, the second moment of area, also called the moment of inertia, but that's geometry. It's got nothing to do with the material, right? So a beam this way has a pretty flimsy eye. If I take the same beam and go like that and try and bend it, right, I can't even bend this thing. The eye is a lot bigger because I'm trying to bend it about the height instead, right? So the actual shape of the cross section itself, the geometry changes the I. If I take E and I multiply by I, that entire thing represents really how rigid the beam is, right? So I can have a combination of material and geometry that makes the beam rigid. That's E multiplied by I. So that's why we call that flexural rigidity. Okay, but the point is, these are just numbers, right? They don't vary with X. So what I'm going to do is take this out front, P divided by 48 EI. Okay, and now I need to take the derivative of this polynomial. Okay, and so, help me out. What's the derivative of 4x cubed? 12x squared, right? The 4 stays out front. X cubed becomes 3x squared. So this is 12x squared. Okay, and how about 3L squared times x? 3L squared. It's just the 3L squared. This is x to the first power. 3L squared is a constant, right? Frequent mistake students will make, they'll take the derivative of this L, right? And they'll say it's 2L. No. L is the length of the beam. It's a parameter. We're taking derivative with respect to x. So the L in this case is a constant, right? So it's minus 3L squared for the constant. Derivative of x with respect to x is just 1. Okay, so that's it. All right, so I get that guy right there. And so question is, can I simplify that at all? I can pull a 3 out of there, right? So if I pull out a 3, I'll have 3 over 48, which is how much? 1 over what? 1 over 16. So I'll have P over 16 EI. I've pulled a 3 out. Okay, and if I pull a 3 out, how much do I have in the first term there? Yeah, I'm going to have 4x squared, right? And I'll have minus L squared right there. Everybody good with that algebra? Just factored a 3 right out, canceled the 48, made it a 16. All right, so that's dy dx right there. Okay, so if I want to find the flat spot, I take that and I do what? Yeah, so if I set theta of x equal to 0, okay, well, that's going to be P over 16 EI times this guy, 4x squared minus L squared. Is P over 16 EI equal to 0? Only if the load is 0, right? Incidentally, if the load is 0, what's the slope of this thing? 0, right? It's straight. Okay, so that's fine, but that's the trivial answer, so that doesn't matter. Okay, and so the possibility here is just this guy, 4x squared minus L squared equals 0. What am I trying to solve for in this equation? X, right? It is the location at which the flat spot occurs is what you get when you set the derivative equal to 0. Okay, and so, great, so I'm going to have what? 4x squared is equal to L squared. X squared is equal to L squared divided by 4. How many answers to that are there? 2 answers, right? X is going to be plus or minus the square root of L squared over 4, which is what? Plus or minus L over 2. Are there 2 physical answers to this problem? Here's the domain, right? Is x equal to minus L over 2? Is that located on the beam anywhere? No. Okay, so this is something to think about, right? In general, when I have a physical problem and I represent it with an equation, My physical problem has a physical domain. The math might exist outside of that physical domain, right? You got to limit your attention to where I actually have a beam. Okay, so just because there's two answers to this math doesn't mean there's two answers to this beam, right? There's only one answer to this beam because minus L over 2 is not on the beam. Okay, and so this means that Y max is occurs, right? So Y max occurs at x equals L over 2. So again, you guys already knew this before we did it, right? So the whole point in engineering in general, if I can answer a physical question and I don't have to use calculus to do it, that's fine. Okay, here we're just illustrating how if I do use the calculus, I get the same location that I knew had to be the case. Right? So, Y max then, I'm going to get the value by doing what? Sorry? Substitute into the original equation, x is equal to what? Yeah, so I want y evaluated at L over 2, not multiplied by L over 2, evaluated. All right, and so what I'm going to get here is P over 48 EI. Okay, and I'm going to plug in an L over 2 wherever I see an x. So it's 4 L over 2 cubed, all right, and then minus 3L squared times L over 2. So Y max is going to be, if I put the P over 48 EI out front, L over 2 quantity cubed is what? Louder? L cubed over 8, right? So L cubed over 8 times 4 is what? L cubed over 2, right? This is L cubed over 8 times 4. 4 cancels the 8, gives me a 2. So that's L cubed over 2, the first term, minus the second term. I'm going to get what? 3L cubed over 2? So I got L cubed over 2 minus 3L cubed over 2 gives me what? It just gives me 1 L cubed over 2 negative, right? So I'm going to get minus one L cubed, right? So minus 3 halves, it's negative L cubed. So I'll get minus P L cubed over 48 EI. Okay, and that is the answer for the maximum deflection. Why is that a negative value? Yeah, it's just because of the way I chose the system, right? In fact, in a purely algebraic mathematical sense, that's actually the minimum value of the function, right? Second derivative here would be what? Positive or negative? Second derivative tells me what about a function? Concavity, and this is concave up. So the second derivative is concave up. It's a min from an algebraic standpoint, but when I talk about deflection in beams, I mean the biggest overall deflection, right? So the negative, that's why we call that the Y max. Okay. Questions?
What are the units on that?
So that's a good question. What do you think? Meters. Inches, right? It's distance. Okay, so again, each one of these parameters will have units built in. Okay, and so if you remember, again, in this class, getting to the point where we're holding you responsible for what is an E and an I and all that, you're going to get plenty of that as you move forward. Right? So as far as you're concerned here, it's a group of letters. I want you to understand what it basically means, but the units are built into the parameters for a problem like this. So you don't have to put a unit here because this isn't a number. So if I put numbers in, then if I put, for example, P in pounds and L in inches and E in PSI, pounds per square inch, and I in inches to the fourth, if you do the math on all those units, you're going to get out just inches when you're done. Okay, if I were in SI, I would put in newtons for pounds, I'd put in meters for the length, I'd put in pascals, newton per square meter for the E, right? And then I would put in meters to the fourth for the I. And when I did all of that, I'd end up with just meters at the end. Okay, but the beauty of these problems, if it's all letters, well then you can't screw up the units. The units are built into the letters. Okay, it's a good thing. All right, so next question. What's the slope at the end x equals 0? Do I need more calculus to answer this? Do we already have the slope? I've got the slope, right? We already took the derivative. Isn't it that guy over there? P over 16 EI times 4x squared minus L squared. So if I want the slope at the end x equals 0, what do? Yeah, I evaluate this thing at x equals 0, right? So I want theta of 0, not theta multiplied by 0. Theta evaluated at 0 gives me P divided by 16 EI. And I put a 0 where? Wherever the x is, right? So it's 0 minus L squared. So, looks to me like theta, okay, evaluated at the left end, theta of 0, is going to be minus PL squared divided by 16 EI. By the way, how can I do a sanity check on whether or not the units are right on this? And also the sign, right? SIGN. Does that negative sign make sense for this guy right here, right? This is the theta of 0, right here at the left end. This angle. Negative makes sense? Yeah, right? The slope is down. It's a negative angle because the y is up, right? So this is a concave up, right? The y is up. The angle's down at the left end. Okay, so what about the units then? Let me ask you a leading question. You already asked me. What are the units on this one? Length, right? So meters, inches, whatever. Length. Units on this correct? Radians. How can you tell by looking at the letters? You got a formula now. How can you tell that these units are right if that one over there is units of length? How do you know this is units of radians? Good. Why would the units cancel out? So you said this is dimensionless. Why is it?
Because you have the force times distance squared, and then on the bottom you have force and distance squared.
Okay, so, but just comparing those two, right? If that's got units of length, that's got an L cubed, right?
Yes.
This has an L squared. So basically it's one order L less. The rest of the letters are the same, right? So again, always when you work problems in engineering, you got to be doing sanity checks all the time. You're going to be cranking out calculations all the time. You can make mistakes at a gazillion places. So constantly be second guessing what you did, look at it, do the units make sense, does it pass a sanity check, what's the number, right? Later on, if you're a mechanical engineer, biomedical, you work beam kind of problems in design, right? You'll have numbers in there. You know, does the result make sense? Did I just determine that the solid aluminum prosthetic just deflected 4.5 inches? Does that make sense? Right? And so doing sanity checks, or should it be, 4.5 thousandths of an inch, right? Understanding like what's reasonable physically. Okay, but problems with just letters and no numbers, you can always check for dimensional consistency. Okay, good. All right. One more beam problem, and then we're going to talk about breaking stuff, which is also fun. All right, so one more. Let's put a beam on here, also simply supported. Okay, so pins at the end. Okay, and let's see. So this is Y. This is x. I'm going to put a sine wave on here, like this. Okay, so it is a sinusoidal load. Okay, length of this thing is L, as always. Okay, and so what would a sinusoidal load look like? It's a distributed load Q of x. Okay, and here's the thing. If the maximum value of that load is some number W naught, then I would argue that this equation needs to be W naught times the sine of pi x divided by L. So before you even solve this problem, okay, I didn't even ask the question yet, but can somebody give me a sanity check on this equation? I mean, how do I know there's not a typo here? Does that equation make sense? What would be some sanity checks to check about that equation? Yeah, I'm showing you the picture of the load, right?
Wouldn't the W naught be the weight wherever it is on the sinusoidal line?
The weight on the sinusoidal line.
Or is that not weight?
Well, I mean, it's a value. I'm calling it W. A lot of times we'll use W to represent a weight. So that's one thing to think about. I mean, that this is a distributed load, right? Do you guys remember what the units are in a distributed load? It's actually force per unit length, right? Force per unit length. So, you know, I don't know about weight. It is a intensity of the load. Look, your next test is about sinusoids, right? So forget the context here. This is a sinusoid, right? What's the amplitude? W naught. So on this picture, what does the W naught represent? The maximum value, right? In terms of the load itself, this is the height, W naught, right here, right? It's the amplitude, so it occurs right there in the middle, right? Should. So what would be the middle? What x value? L over 2. Can I check the equation to see, does that make sense? Let's put in L over 2. Pi, L over 2. I'm going to get the sine of pi over 2, right? Which is equal to? See how the trig never goes away, right? Warned you about this. Sine of pi over 2 is how much? 1, right? So this is 1, W naught. Okay, so in the middle, the value of the load is W naught. What about the endpoints? How can I check the equation to see whether or not, you know, this looks right at the ends? What should the value be at the endpoints?
0.
Looks like 0, according to the way it's sketched. How could I check the equation for that? All right, so I can plug in the first one. The left end is what point? X equals 0 over here, right? So this is the sine of 0. How much of the sine of 0? What is that? Is the sine of 0 1? Sine of 0 is 0, right? So I'm going to get 0. How about at this end? What value of x is this? This is x equals L. So if I evaluate the function at x equals L, I'll get what? Sine of pi. What's the sine of pi?
0.
Okay, so we got some sanity check. It's 0 here and here. It's maximum in the middle. That looks like the load that I drew. Okay, and since we're talking about exam number 2 coming up here, right? What's the period of this sine function? Is the period pi over L?
No.
Note, by the way, that we don't have time in this problem. So this is spatial period, right? Not temporal period. This is a sine as a function of x, not time, but it's still, right? You're replacing x with a t. It's the same stuff. What's the angular frequency? pi over L. Okay, so just to be clear, omega, not W, omega is pi over L. How do I go from that to period? So, what? Do you guys remember how you go from period to, how do I go to frequency? Isn't this the same as 2 pi times f? Right? So the pi cancels out, right? Right, so f is what? 1 over 2L. So the period t is what? 2L. Does that make sense? How much of a sine wave do I have plotted here? I got half of one, right? This is the equation of a half sine wave with an amplitude omega. Sorry, W naught. Okay? It's a half sine wave with an amplitude W naught. And so the point is, you can use your knowledge of sinusoids, right, to check that. All right, just couldn't resist the opportunity for review. All right, okay, so y of x. Turns out the answer for this guy is a little messy. It's the following: minus W naught L to the 4th divided by pi to the 4th EI, okay, times the sine, it's another sinusoid, pi x divided by L. That is the answer for the deflection curve. Okay. By the way, what kind of function is that? What's it going to look like? It's a sine function. How's this sine function different than this sine function in terms of the way it looks? It's going to be negative. So what does that do with the way it looks? Yeah, it flips it upside down, right? So, I mean, again, these beam problems are pretty intuitive, right? Here's a load. What's the beam going to do? Well, I'm probably going to do something like this, right? So that's it. It's a half sine function the other way, flipped upside down. The amplitude obviously is a different number than this. This guy has units of what? Length. This has units of force per unit length. The behavior is affected by the E and the I and the L, right? So that's all in there. All right, great. So what I'd like to do is just illustrate how all these derivative relationships work, right? I wrote this all on the board last time about how first derivative is a slope, second derivative with an EI gives me a bending moment, then I talked about a third derivative was a shear force, and all these things. Let's see whether or not those things all work out. Okay, and so let's see if we can find from these equations, I want theta of x, I want m of x, I want v of x, and then it turns out we can keep going from the given result and get the q of x and see whether or not that agrees with the starting point here. So this will be an exercise in taking derivatives, but we'll see how all these relationships work out. Okay. So theta of x, by definition, is dy dx. So I want the derivative with respect to x of the given function, minus w naught L to the 4th divided by pi to the 4th times EI, and then I've got a sine function, pi x divided by L. Help me out. What do I do with the letters in front there? These guys are constant, right? So the minus w naught L to the 4th divided pi to the 4th EI, that just sits there. And now I need the derivative of the sine of pi x over L. Derivative of sine gives me what? Cosine. What about the letters in here?
Pi over L is the sine.
Yeah, so this is like sine omega t, except the t's an x. Derivative of sine omega t is omega times the cosine omega t. The omega is the pi over L, right? That comes out front, so I'm going to get pi over L out front, cosine pi x divided by L. So when I pull that pi over L out front, can I simplify this thing at all? Yeah, it looks like I get 1 less pi and also 1 less what? L. In general, with a beam problem, if I start with a bunch of letters for deflection and I find slope, I always need to get 1 less L. Right? That's the unit thing. Okay? Got to get 1 less L. This is how you get 1 less L here. In a problem that's a polynomial, I get 1 less L because when I take the derivative of an x cubed, I get an x squared. Right? So I get 1 less L that way. So it's a different way of getting 1 less L, but it's still 1 less L. So it's minus W naught L cubed divided by pi cubed EI. Okay, and then I still have this guy, cosine, pi x divided by L. Okay, so that is theta. All right, so how about the moment? Okay, and again, we wouldn't have you memorize this, right? We would make sure if we asked you to do this on a test, we would remind you that m of x is EI times 2 derivatives of y with respect to x. All right, that is called the moment curvature relationship. Okay, second derivative is curvature, essentially, if the angles are small. Okay, and so this is the same as EI times the derivative of theta, right? Because theta is the first derivative. So the derivative of theta would give me the second derivative. So the point is, I just keep going, right? Take this guy, multiply by EI, and take the derivative. So m of x, I got to put the EI in front now, and I start with this times the derivative with respect to x of all of that, minus W naught L cubed divided by pi cubed EI, okay, times the cosine pi x divided by L. What do I do with the letters out in front there? So this EI stays. These letters come out front. What happens to the EI? Cancels out. Minus W naught L cubed over pi cubed. Right? I canceled out the EI. Now I've got the derivative of the cosine. Pi x over L gives me what? Negative. And the omega comes out. What's the omega? Minus pi over L out front, right, times the sine pi x divided by L. Does that look right? So interesting. I got 2 negatives there, which gives me a what? Positive. What happens to the pi and the L? I get 1 less of each, right? W naught L squared up top. Pi cancels pi cubed, gives me pi squared in the bottom. And I'm back to the sine pi x over L. Okay, now, maybe this is during the exam, right? And I'm nervous and I'm going fast and I want to do a sanity check on this. I took one more derivative with respect to x, okay? And I got the moment. The moment is the thing that, causes curvature, right? Bending. The internal load that corresponds to curvature. Okay, so m of x that I got there is a positive number. Does that pass sanity check? This deformation here is going to be what? Concave up or concave down? Concave up, right? So that works, right? The m of x is going to be concave up over the whole length of the beam. So that makes sense. The part about the units, you could double check if you remember this is pounds per unit length, but you'd have to remember what are the units of moment. Again, if you haven't had physics yet or mechanics of any type, might be a hard thing to remember. The EI went away, okay? So going directly from here to that can get a little confusing because the EI goes away when you add that second derivative, okay? But this is pounds per inch times inches squared is pounds times inches. If you had physics, right, moment is what your physics teacher probably called torque. It's force times distance, right? So pounds per inch times inches squared is force times distance, pounds times inches. All right, great. So we got theta, we got m. How do I get the next one? Shear. v of x. Okay, well, it turns out the v is just, by definition, all right, v of x is ei times the third derivative y with respect to x. Okay, now you got to be careful when you look at this. M was already ei times the second derivative. So ei times the third derivative is just the derivative of m. Right? It's not ei times the derivative of m. The m already has the ei in it. Right? This is m right here. So one more derivative of this, the ei stays, I get the third derivative. Okay, and you can do a sanity check on the units, right? Force times distance, derivative with respect to x, knocks the units down, one less. Units on this will be what? It's going to be force, right? So that's what this is supposed to be, shear force. Okay, so that is the shear force, just to be clear. So the units are force. All right, so basically we just need another derivative. So this is derivative with respect to x of this answer right here. W naught L squared divided by pi squared times the sine pi x divided by L. Okay, this thing seems to be getting simpler as we go, which is nice. What do I do with the numbers out in front, the letters? They stay out in front. W naught L squared divided by pi squared. And then I've got the derivative of the sine, pi x over L. It's like Groundhog Day over here. Right? I already did that. So what's the derivative of the sine, pi x over L? Pi over L out front. And I got cosine, right? Pi x divided by L. Okay, and what happens to the pi and the L? I can cancel one pi and one L, right? So I get W naught L over pi, okay, times the cosine pi x divided by L. And I can do a sanity check on these units, because if moment had W naught L squared, and moment is force times distance, then force needs to have one less distance, W naught times L, passes a sanity check, right? All right, and then the last thing you can do, I'm not sure if this is irony or entertainment, okay, is you could take the derivative once more and see whether or not the entire problem was stated correctly, okay, because q of x, by definition, is actually negative dv dx. Okay, that negative is hard-coded in there. Yes, question?
Back to the x, aren't you supposed to multiply it by a di at the end here?
No, so let me back that up. I talked a little about that, but I know that can get confusing. So, by definition, the moment is the EI times the second derivative, okay? The shear is the EI times the third derivative, okay? But, you know, what is that? Here's the moment again. If I just take the derivative of m, not multiply by EI, just take the derivative. The EI is already there, and I get EI times the third. So this expression, EI times the third derivative, is just the derivative of m. So when I came over here to take the derivative of m, the fact that the EI was there, that's already been built into this answer. Okay, so there's no extra multiplying by EI. That comes in right here. Okay, and I'd have to teach you strength of materials to get to the point of why this is. And I'd have to derive where that comes from. But you can take this as a starting point. This is a definition for m, and if I have that, I just take another derivative of m to get the v. Okay, it's a good question. All right, so minus dv dx is the definition, and this minus sign just has to do with sign conventions for internal shear force in relation to external load. Like, so for example, this load is defined as positive, even though you can see that it points down, right? And so it's just the way we chose that definition. If we would have called this negative, then this would be a positive here. Okay, so based on those definitions, I put a negative in front, and so I need minus derivative with respect to x of what I just got for v, which is W naught L divided by pi times a cosine pi x divided by L. So what do I do with the W naught L over pi? Comes out front, have a negative, so it's minus W naught L over pi. I need the derivative now of the cosine, pi x over L. So I'm going to get negative, pi over L comes out front, that's the omega, times the sine, pi x divided by L. What happens to the pi and the L? And the negative? They all cancel out. Negative, negative, pi L gone. W naught times the sine, pi x divided by L. Okay, and that, of course, was the Q that was indicated in the problem statement. Okay, so the fact that I got that at the end is basically a statement that I wrote this answer down correctly as the starting point. Okay, if I would have made a typo here, this would have been the check on that, right? I couldn't have got the right answer if this was wrong. Beam deflection, any questions on that? Okay, so we always like to put a beam problem. Beam problems are good because, you know, you can really just think about what the deformation, look at the picture, think about the deformation. Okay, incidentally, if you look at all of the posted exams, all of them are asking you to sketch the deformation of the beam. And so, again, a lot of times, you know, what we'd like to do is have the math help you understand the deformation, right? So we're having you find slopes, find maximums, find places where deflection's 0, so you've got analytical information to sketch it. But you might screw up the math, right? It's an exam. So you might screw the math up. You can screw up the math and you can still sketch that beam properly, okay? Because we're asking you to be an engineer, right? So just look at the picture and say, does it make sense with my math? If I've got a beam supported like that, and I asked you to calculate the deflection at x equals L, okay? And you got some number like, I don't know, W naught L to the fourth over pi to the fourth EI times 12. Okay, you got that number for the deflection at this point. Is your answer right or wrong? It's wrong because it's pinned at this point, right? I mean, forget your math, just look at the picture. So in the end, I hope the math on the test helps you sketch the picture correctly. If the sketch that makes sense to you agrees with your math, you should feel happy at the end of that problem. Okay, if your math is like, there's no way the beam does that, then if I were you, I'd feel disturbed. Doesn't mean your grade's bad. It means you made a sign error or a derivative error somewhere. You might have lost a couple points. Okay, you could still sketch it. All right, we get students all the time like, this makes no sense. Part D is blank. Really, you want to take a 5-point hit on a sketch just because you know that your answer for the numbers is wrong, right? So look at the picture, think, if I were a beam, how would I deform? Okay, and draw the picture. Okay, this is my advice. It's worth 5 points. It's worth 5 points. Okay. This is a part that's now fun. We're going to talk about why stuff breaks in a very introductory way. Okay, and we're going to talk about concept of stress and how we can see where derivatives might be used in this. But we're maybe only going to use the derivatives when we have to. They don't have to be used all the time. Okay, so again, here's an example. This is stress, right, under what we call axial load. Incidentally, when I cooked up the course materials for this class, it was me and Dr. Rattan, right? We wrote the book on this, and so we developed these course materials back in like 2004. And this little section right here, these couple pages, is literally, it's just 2 pages I took right out of my own strength and materials notes. Okay, so this, exactly what we're going to do here is what we cover again in strength and materials, thinking about what breaks things. Okay, and so what do I mean, number one, by stress? And what do I mean by axial loading? Got to make these points. Okay, so let's say that I've got some bar, and I'm drawing it here like it's a rectangular bar, but it could be circular, it could be any cross section that is uniform. Okay, and I put a load on this bar, okay, a load P. On both sides. So this thing, you know, strength of materials is about how things deform when they're under load. The loads generally we consider are in equilibrium, right? So we're not trying to do some complicated statics. We're saying if I pull on this bar, is it going to break? Okay, and so let me ask you first a question. If I pull on a bar that's made of steel. How much load does it take to break it? You give me a number?
We don't know.
What don't you know? How thick it is. Okay, well, so, right, how thick it is, what's the failure property. Okay, besides the thickness, what else probably matters? Does the length, how long it is matter, do you think? If I'm just pulling on it, the bar is half as long, and I knew a certain load would break it. If I take the bar half as long and put the same load, can I still break it? Probably. So probably not the length, but somebody said thickness. Thickness to me is this dimension. It's probably the width, right? So isn't it true that to break this, it's not really how big is the load, it's how much load do I have that acts on the cross-section of the material, right? So inside this thing, the cross-sectional area is what is having to resist that load. Okay, and so this cross-sectional area inside the material now is what I'm going to call A. Okay. So turns out what breaks things is actually values of stress. Okay, and what normal stress is the stress that occurs when I load something axially. Normal means perpendicular. That's what the word normal means. Okay, so stress perpendicular to the cross-section. Okay, and so it turns out we use the Greek letter sigma for stress. And what it is it's the intensity of the force. It's the force P divided by the area. Okay, so this is force per unit area. So if I am in English units, this is pounds per square inches, which is what we also call PSI. What else is measured in PSI? Pressure. Air in my tire. Okay, now this is being pulled. Pressure pushes on things, right? So if I pressurize something, it's pushing on it from the inside, okay, but it's still pushing on it, right? So yeah, it's the same physics, right? Pressure is just stress. Pounds per square inch. If I'm in SI, it's Newton per square meter. Anybody know what the derived unit's called for that? What's a Newton per square meter? It's a Pascal. Okay, may have had that in high school physics, maybe not. Okay, so that's a PA. All right, great. So I got intensity, right? So the idea is it's not just the load, it's how big's the area. All right, so here's the question I want to look at, kind of illustrating why do we need any calculus to think about whether or not this bar is going to break. Okay, and here's the thing. You know, I happen to choose a coordinate system here where I line this thing up with the x direction. And in fact, the y doesn't even matter for this problem because I'm just loading it, it's one dimensional, right? I'm just loading it in the x direction. Great. If I'm a piece of material, okay, inside the middle of this bar, do I have any idea which way I'm facing? I think about it. If you drilled way down inside, okay, let's say this bar is actually, you know, wood, and you're a termite, okay, and you go inside the middle of this bar, and you're eating your way through, you have no idea which way this thing's being pulled, okay? So the point is the coordinate system is made up. It's made up by the person that drew the schematic. It's completely made up, okay? And so if I start trying to define whether or not this breaks based on my made up coordinate system, how do I know that what I'm even doing here is the worst thing that I'm doing to the material? Like, I mean, I could look at, you know, normal to it this way. I mean, what if I looked at it at some other kind of angle, right? Like, so for example, you know, what stress values or what stresses act on other planes, right, in here? All right, so I drew one plane and I defined the stress, P over A. Great, that seems like it's got the right characteristics. But I mean, can I worry about if I take the same bar now, okay, and okay, when I pull on this thing now, okay, what if relative to straight up and down, what if I sliced it this way? Okay, and so now Okay, I've got, this business going on. Okay, and so instead of the plane straight up and down, what if I'm worried about what's the stress acting on a plane that's at an angle like that? Okay, where the angle I've cut this at is now an angle theta. Okay, so same exact bar, same loads P. Now I want to think about theta that's not straight up and down now, okay, but it goes like this. Okay, and keep in mind that the original area, A, in the stress formula, that's like the vertical leg of this triangle here, right? If I just multiply by the width, I'll get a vertical area, right? And then this guy at an angle is a different number, right? It's A theta. Incidentally, how does A theta compare to A? A theta is the hypotenuse area, right? A is the adjacent leg area. So how are they related? It's a cosine relation, right? I mean, specifically, it's A is A theta times the cosine theta. So that would mean A theta is actually A divided by the cosine of theta, right? By the way, does it bother anybody that I'm using areas and talking about triangles? This bothered me the first time I saw that. Are you guys okay with that? Right, I mean, if it's just the triangle is just this front projection of it, right? So the lengths of these sides clearly are related by the cosine. The area is the length in the plane times the width, right? The thickness of the bar. So the areas are the same numbers with just scaled by the thickness. All right, so that's the reason why this area scales with that area by the cosine. It goes the same way the length goes. The thickness is the same. Yes? Good with that? All right, so what does this mean? I could do a little more algebra to show what happens. I'm going to cut to the chase on the net result. Okay? Turns out that because I have now a different area, right, and I have now forces acting in more than one direction, let's just cut this thing right here, okay, and let's see what's happening on the inside here. Okay, and so this is now my A theta. Okay, and so if I just draw the two-dimensional view now, I've got the P over A, for the stress. This is a stress picture. So in this direction, I got sigma equals P divided by A. Okay. Now keep in mind, this force is going in the horizontal direction, right? If I come over here on an angle now, and I want to talk about normal stress, normal means perpendicular. So is it going this way? Now, I mean, if I've got a normal stress is the stress by definition that would be normal to that area. So I know I'm going to have this guy. Now, this isn't forces. This is a stress diagram. How do I go from stress to force? This is stress. This is force, right? I multiply the stress by the area. So I could turn this into a force diagram by saying, look, this is force if I just take sigma theta times this area, which is A theta. This is force P, I already know, right? The vertical area is A. Great. Okay, is this thing in equilibrium like this? What's the problem with this? If this is the only forces, right? Again, it's a stress picture, but if that's the only forces that act, what's this thing going to be doing? It's going to be accelerating upward and also what? To the left, in other words, like rotating. Right? This thing is not in equilibrium. This thing's going to be accelerating up and spinning. Right? And how do I know that? Because it's got a net force in the y direction. So the whole thing's going to be accelerating up. And these forces aren't coincident. So I could think about force times distance, which will give me a moment, which will make it spin. Okay? It's not in equilibrium. So to make this equilibrium, whatever's happening here, which clearly, this is the way the real problem's loaded. This is in equilibrium. So if I just come in the middle of this real problem and look at it at an angle and sketch just that part, this half of this beam, has to be in equilibrium also, right? So if this is up and to the left, and this thing's just left, what do I also need here so that it balances it? I'm going to need it down and to the right on here, apparently. Okay, I'm going to need like this. So if I look at an angle, key point, normal stress is not the only thing I have. I have to have something that looks like it's sliding, right? I need to have sliding inside the material in terms of a force. A sliding stress is what we call shear stress. Okay, and so what I end up with here is actually shear. We use the Greek letter tau to represent shear stress. I'm calling it tau theta because it's at that angle. Okay, and so here's the bottom line. Turns out sigma theta is the original sigma, this one over here, P over A, times the cosine squared of theta. Okay, the tau theta is the original sigma, okay, times the sine of theta times the cosine of theta. Okay, and the way you get that is you take the corresponding forces and you divide them by the corresponding area, and of course that area is not the original, right? It's A over cosine theta. So that's how you end up with a cosine squared there and a sine and a cosine there. So this is the background. Where does calculus maybe come in? If the stress is different at different angles, then what angle do you think it'll break at? The angle where the stress is greatest. It sounds like a calculus problem. Okay, so that's it, right? I mean, where is the stress maximum? Okay, and so the question is, at what angle, okay, is the stress maximum? Okay, and even that, which stress am I talking about here? Am I talking about the sigma? Or am I talking about the tau? Let me throw in a piece of observation. Okay, I'll call this a note. Brittle materials, they fail where sigma theta is max. Okay? So a brittle material is a material that can't deform a lot, something I can't bend, something that would prefer to just snap in two as opposed to bend into a different shape. Give me an example of a brittle material.
Cast iron.
Cast iron is a good one, right? You see the signs at the gym, don't drop the weights. It's because you take brittle material and you drop it, and if it has a crack, then all of a sudden you got two pieces of weights, right? You see this all the time in the cast iron weights with the head laying on the floor. Somebody trying to lift weights that they literally can't set down. Okay, it means you should use less weight. All right, so that's just a pet peeve of mine. All right, so brittle materials favor when sigma theta is max. Okay, and what else? What else besides cast iron do you think? Glass.
Yeah, glass.
Ceramic, right? Ceramic, we use ceramic tiles on the space shuttle. Certain kinds of plastic, right? Depending upon temperature. Yeah.
Well, dried clay.
Dried clay, sure. All right, so we got brittle stuff. On the other hand, this is key. So this is point one. Okay, ductile materials, these guys fail where it turns out that the tau theta is max. Okay, and so what do I mean by a ductile material? A ductile material is a material that when I load it, right, past its elastic limit, I can now bend it, right, like a paper clip. I can take a paper clip and I can just bend it, and now I have a bent paper clip, right? I don't have two pieces. If that paper clip was made out of glass, right, it would just snap in two. So that's the difference, right? So what kind of materials do you think are ductile?
Copper, steel.
Rubber's a hard one because you're thinking about elastic, right? Rubber, I bend the heck out of it, and it doesn't snap in two, but when I let go, is it still bent? It bounces back. So that's an elastic issue. That's not what I'm talking about. It's a different issue. Steel. Aluminum.
Copper wire.
Copper. Nickel. Tungsten. Titanium. Zinc. Metals in general, unless they're processed in a way that makes them brittle, like casting, all right? Cast iron ends up brittle. Okay, so it depends on the processing, but steel, everything's steel, pretty much ductile. Although, if I make the hull of my ship steel and I sail it in the Arctic Ocean,
Yeah, very dense ship.
you know, it depends on temperature. If I heat things up, they tend to be more ductile. If I make things really, really cold, they tend to be more brittle. All right, so far none of this is calculus. All right, so let's do some calculus. So, you know, what does this mean? I might want to think about, you know, where would be the maximum load? And so I've got some stuff in here for each of these stresses. Let's take a look at tau theta. Let's suppose this bar is made out of steel. Okay, so if it's steel, then I care about where tau is max. So for example, right, steel bar, okay, what I want is I want tau theta, right, max. Okay, where is the maximum value of tau theta? So can we do calculus on this? Tau theta is the sine of theta times the cosine of theta, right? And then I have the sigma in front. So it's the original stress times the sine times the cosine. If I want the maximum value, what do I want to do with this function? Set the function equal to 0, the derivative equal to 0. So what I want to do is I want to set the derivative of tau theta with respect to what? Do I have an x here? Do I have a time? I got a sigma. What's the sigma equal to? P over A. So I know what my bar is. I know what my force is. Is the sigma a variable here? It's a constant, right? It's a parameter. So I'm taking the derivative with respect to what? It's the angle, right? I'm trying to figure out at what angle does this occur. Okay? Equal to 0. Okay, so let's do that. Derivative tau theta with respect to theta is what? Well, I got some choices here. This is a sine times a cosine, right? So to take that derivative, I could use a product rule. First derivative of second, second derivative of first. I'm going to get more sines and cosines. This is going to get easier or harder? Maybe harder. Can I do some trig on this first to make my life easier? It's a double angle. This is like a sine of 2 theta, right? But if it was a sine of 2 theta, there'd be a 2 here, yes? Sine 2 theta is 2 times the sine theta cosine theta. So if there's no 2 here, then I need to do what? Sure, this is sigma over 2 times the sine of 2 theta, right? Boy, that's a lot easier. So let's take the derivative. Derivative with respect to theta, let's use the easy one. I got sigma over 2 times the sine of 2 theta. So what's the derivative of that? What do I do with the sigma over 2 there? That stays out front. So this is sigma over 2 out front. Derivative of sine is what? Cosine. What about the 2? So this is 2 times the cosine 2 theta, right? Okay, so this is the same as sigma times the cosine 2 theta, right? And I want to do what with that? Set it equal to 0. And I'm trying to solve for what? So the question is, when is the cosine of 2 theta equal to 0? And here's an interesting note. Isn't that the same place as where the sine of 2 theta is equal to a maximum? And so did I even need calculus to answer this? This is a trig function, right? The maximum of a trig function is what? It's the amplitude, right? This is between -1 and 1. Now, what angle does it occur? Well, it occurs when the cosine 2 theta is 0, or when the sine 2 theta is max, either one of those things, right? Sine 2 theta is 1. Either one of these statements tells me that 2 theta is what angle? 2 theta is what angle? 2 theta is pi over 2, right? Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Right? The flat spot occurs where the sine function's maximum. That means theta is what? Pi over 4, which is 45 degrees. Okay? By the way, the maximum value of tau max is what? When this is 1, right? Tau theta max occurs when the sine is 1, right? It is half the normal stress, sigma over 2, at theta equals 45 degrees. So this means that if I take a ductile bar like titanium, right, or steel, and I pull on it all the way until it starts to stretch, like noticeably, I can see it stretching in the machine, and it breaks in 2 pieces, what angle is it going to break at? 45 degrees, because the shear causes that. Now, I know you're getting antsy on the clock. Just take me 1 second. I can load things different ways besides axial loading. Like chalk over here. Chalk is basically little mini shafts. Okay, it's a shaft. It's round, circular, and I can put a little like imperfection on it because that makes my experiment easier. And then, I can think about a shaft that instead of pulling on this thing, because you'd have to be really strong actually to pull a piece of chalk until it broke. Okay, just to be clear. The guy that drops the weights at the gym, he can't break it that way. All right? But you could take this thing and you could twist it. Okay? You could twist it. It's the same reason why, like if you're playing sports, again, and you plant your arm or your leg and you twist it, okay, until you get a break. That's called a biomedical engineer. You got to worry about this. It's a torsion break. That's not pretty. Okay, here's what happens when you twist something that's brittle until it breaks, right? Take a look at this. Can we see?
Yeah.
Does that thing break straight across? It breaks at what angle? It's a helix. By the way, I got a whole thing of chalk here. Anybody that wants to break some chalk here, please. Please. But you want to break it by twisting the chalk. You might want to put a little nick in it. Anybody you want one? Break some chalk. Bring the broken chalk with you. The point is chalk is what kind of material? Ductile or brittle? Brittle, but I'm not pulling it. I'm twisting it. So I'm changing the problem. I'll assign this one for homework. Okay, it's in the book. But what happens with stress when I twist things? And you should have some sense of, where it breaks. Whoever wants to twist chalk until they can break it. Anybody else want to try? I got a few pieces left. Anyone? Is that asking for chalk or a stretch?
No, that's
2 more chalks. You want to twist it. Don't bend it. Twist it till it breaks. I got 2 more. The end. Bring the broken chalk with you. 2 more for you ladies. Okay, twist it till it breaks.